Today, the North Pole is one of the coldest and most inhospitable places on Earth. But imagine a time when this icy wilderness was a tropical paradise with lush forests, flowing rivers, and crocodiles sunbathing by the water. How could this be possible? Let's journey back to a time when crocodiles lived near the North Pole. To understand how crocodiles once thrived at the poles, we must first dive into the remarkable climate conditions of the Eocene epoch, an era when Earth was a greenhouse world. This term describes a time in Earth's history when global temperatures were significantly warmer than today, creating a climate vastly different from what we see now. The Eocene epoch began approximately 56 million years ago and lasted for about 22 million years, during which global temperatures averaged 10 to 15 degrees Celsius higher than today. Fossil evidence and climate modeling suggest the Arctic experienced summer temperatures between 20 and 25 degrees Celsius, or 68 to 77 degrees Fahrenheit, warmer than many regions of the modern world. Sediments collected from Arctic drilling sites have revealed astonishing clues. One study conducted at the Lomonosov Ridge in the Arctic Ocean uncovered fossilized pollen, leaves, and tree resin, or amber, indicating that the region supported dense temperate forests. These findings, published in Nature in 2006, provide direct evidence that the Arctic was frost-free and verdant. Unlike today, where glaciers and ice sheets dominate the poles, the Eocene poles were entirely ice-free. Higher sea levels, estimated to be 70 meters or 230 feet higher than today, flooded large areas of the continents, creating shallow, warm seas that further amplified the greenhouse effect. At the heart of the Eocene's greenhouse conditions were high concentrations of carbon dioxide in the atmosphere. Geological records suggest CO2 levels were between 1,000 and 1,500 parts per million, 3 to 4 times higher than today's levels of around 420 parts per million. Massive volcanic eruptions, particularly in regions like the North Atlantic igneous province, released immense quantities of CO2 into the atmosphere. These eruptions coincided with the early stages of the Eocene and contributed to the sustained warmth. Another major contributor was the release of methane, a potent greenhouse gas, from seafloor deposits during the Paleocene, Eocene thermal maximum. Methane released from undersea hydrates likely triggered rapid warming, and as methane oxidized into CO2, it created a runaway greenhouse effect. During the Eocene, the positions of continents and the absence of polar ice caps allowed warm ocean currents to circulate more effectively, transporting heat to the poles. Without ice sheets to reflect sunlight, the dark ocean waters absorbed more heat, further amplifying global temperatures. At the time, the continents were still drifting into their modern positions. The North Atlantic was just opening, and Antarctica had not yet separated from South America and Australia. This configuration prevented the formation of cold, isolated ocean currents like today's Antarctic Circumpolar Current, which now helps keep Antarctica frozen. The Arctic Ocean itself was more like a giant, warm lake. Fossil evidence of marine algae and microscopic organisms called dinoflagellates suggest that surface waters were as warm as 22 degrees Celsius or 72 degrees Fahrenheit during the summer. Picture a landscape of dense forests, teeming rivers, and a warm, humid climate. This was the polar world of 56 million years ago, a tropical heaven unlike anything we could imagine in these regions today. Fossil evidence paints a vivid picture of what life was like at the poles during the Eocene. These regions supported ecosystems more similar to modern-day subtropical or tropical environments than the frozen tundras we associate with the poles. Among the most remarkable creatures found near the ancient Arctic Circle was Borrelosuchus, a genus of extinct crocodilians that once patrolled the lush rivers of what is now Arctic Canada and Greenland. These reptiles grew up to 4 meters, or 13 feet, in length and weighed several hundred kilograms. With robust jaws and sharp, conical teeth, Borrelosuchus likely hunted fish and small mammals along the river banks. Like their modern relatives, they were cold-blooded, which means their very presence in the Arctic underscores just how warm the poles were. Because without consistent tropical temperatures, they simply couldn't survive. Large freshwater turtles were another staple of the polar ecosystem. While the frog, like Palaeobatrachus, also existed, it was not a turtle. The Eocene polar regions hosted diverse turtle species, including ancient relatives of modern softshell and snapping turtles. Some of these giants measured over a meter, or 3.3 feet, in shell length. They thrived in the warm, slow-moving rivers and swampy wetlands, basking in the sun and feeding on aquatic plants, insects, and small fish. Early mammals also made their home in these high-latitude jungles. Coryphodon was a hippo-sized herbivore, weighing up to 500 kilograms, or 500 pounds, and measuring around 2.5 meters, or 8 feet, in length. With broad, flat teeth, it likely fed on soft vegetation in the swamps and forest undergrowth. In contrast, Leptictidium was a small, agile insectivore about the size of a modern-day ferret, only 60 centimeters, or 2 feet long. With long hind legs and a pointed snout, it likely darted through the forest floor foraging for insects and small invertebrates. Together, these mammals revealed the wide range of niches supported by Eocene polar ecosystems. Eocene skies and wetlands were alive with bird life. Presbyornis was a long-legged wading bird about 1 meter, or 3 feet, tall, resembling a hybrid between a duck and a flamingo. It thrived in shallow wetlands, filtering food from the water like today's dabbling ducks. More imposing was Gastornis, a flightless giant towering up to 2 meters, or 6.5 feet, tall and weighing over 150 kilograms, or 330 pounds. With a massive beak and powerful frame, Gastornis dominated the forest floor. Once thought to be a predator, recent evidence suggests it was herbivorous, using its formidable beak to crush tough plant matter and possibly defend itself from predators. The warmth and vegetation also nurtured a vibrant insect community. Amber fossils from the Arctic reveal ancient bees, flies, beetles, and ants, key pollinators and decomposers in the ecosystem. These insects filled essential roles. Bees pollinated flowering plants, beetles helped recycle organic matter, and flies sustained birds and small mammals. Their fossilized forms, trapped in golden resin for over 50 million years, give us a direct glimpse into this long-lost tropical paradise. Perhaps the most vivid evidence of a tropical Arctic comes from the plants. Fossilized palm leaves, magnolia flowers, and delicate fern fronds have been unearthed in sediment cores taken from sites like Ellesmere Island and the Lomonosov Ridge. These weren't just a few scattered plants. They were part of towering forests, dense undergrowth, and tangled canopies resembling modern subtropical jungles more than anything we'd associate with the North Pole. Swampy lowlands cradled water lilies, cattails, and other aquatic vegetation. These shallow, sunlit waterways nurtured fish, amphibians, and turtles while supporting birds and mammals on their banks. The wetlands were crucial biodiversity hotspots in this ancient ecosystem. From sticky tree resin came amber, nature's time capsule. Inside these translucent stones are grains of pollen, fossilized spores, and even perfectly preserved insects. Analyzed under microscopes, these specimens allow scientists to reconstruct what plants bloomed in the Arctic summer and which insects buzzed through the canopy. Together with data from sediment layers, they reveal an Arctic that was not only warm but alive with diversity. Research into polar life during the Eocene continues to uncover new surprises. Studies like the 2006 Arctic Coring Expedition, or ACX, which drilled deep into the seafloor near the North Pole, have provided invaluable data on the climate, flora, and fauna of this ancient world. In 2014, a groundbreaking study published in Proceedings of the National Academy of Sciences analyzed fossilized plants from Arctic sites, concluding that the region experienced a humid subtropical climate with year-round warmth. These findings challenge our perceptions of what the poles are capable of and highlight the profound effects of a greenhouse climate. For millions of years, the poles thrived as tropical havens. But no paradise lasts forever. By the end of the Eocene epoch, Earth underwent a dramatic shift. The greenhouse world began to cool, marking the end of the tropical poles and the dawn of the icy landscapes we know today. What triggered this transformation, and how did life adapt to a cooling planet? The cooling of Earth was not the result of a single event, but a cascade of interconnected processes that unfolded over millions of years. Beginning around 34 million years ago, as the Eocene epoch gave way to the Oligocene. One of the primary drivers of cooling was the steady decline in atmospheric carbon dioxide levels. Geological processes, like the weathering of silicate rocks, pulled CO2 out of the atmosphere and trapped it in the form of carbonate minerals. Without high Q2 levels to trap heat, Earth began to cool. A 2018 study published in Nature Geoscience found evidence that this decline in CO2 was accelerated by the uplift of mountain ranges like the Himalayas, which increased the rate of weathering and carbon sequestration. While the Arctic remained ice-free for several more million years, the cooling Earth had its first major impact on Antarctica. The separation of Antarctica from South America and Australia created a new oceanic pathway, the Antarctic Circumpolar Current. This current circled Antarctica, cutting it off from the warm equatorial waters that had previously reached its shores. As a result, the continent began to cool rapidly, and the first ice sheets formed around 34 million years ago. Once ice began to form, it reflected sunlight back into space, amplifying cooling in a feedback loop known as the ice albedo effect. This process accelerated the growth of ice sheets and drove temperatures even lower. At the same time, the shifting positions of continents played a pivotal role in cooling the planet. By the late Eocene, the plates carrying North America, Europe, and Asia moved closer to their modern configurations, altering ocean and atmospheric circulation patterns. The narrowing and eventual closure of the Tethys Sea, a vast body of water that once separated Europe, Asia, and Africa, disrupted the flow of warm currents to the poles. This restricted heat transport and further cooled the high latitudes. Though the Arctic remained free of permanent ice for millions more years, Its cooling was influenced by the same tectonic shifts that isolated Antarctica. The Arctic Ocean became less connected to the warmer Pacific and Atlantic waters, making it increasingly susceptible to temperature drops. For the plants and animals that thrived in the tropical poles, the cooling climate was an existential threat. Many species were forced to migrate closer to the equator, while others faced extinction. Cold-blooded animals like crocodiles could no longer survive the cooling temperatures of the Arctic. Fossil evidence shows they retreated to regions with more stable, warm climates closer to the equator. The tropical forests of the poles also disappeared. Fossilized tree stumps found in the Arctic show that as temperatures dropped, these trees struggled to survive the harsher winters and shorter growing seasons. Eventually, they were replaced by tundra and steppe vegetation. The cooling poles also transformed marine ecosystems. Warm water species disappeared, replaced by cold, adapted organisms better suited to the changing conditions. The Arctic remained ice-free longer than Antarctica, but cooling continued into the Miocene epoch. Permanent sea ice in the Arctic began forming around 2.25 to 3 million years ago as Earth entered a new phase of glaciation. Changes in Earth's orbit, tilt, and axial wobble, known as Milankovitch cycles, triggered glacial periods during which ice expanded across the poles. These cycles, combined with lower CO2 levels, solidified the Arctic's transformation from a tropical haven to a frozen wilderness. The end of the tropical poles reminds us how dynamic and interconnected Earth's climate system is. It also serves as a warning: the processes that cooled the planet took millions of years. But today we are seeing the reverse warming driven by human activity occurring in mere centuries. The ice caps we see today are relatively young in Earth's history, and their existence depends on the delicate balance of atmospheric CO2, ocean currents, and global temperatures. Disrupting this balance could return Earth to a state resembling the Eocene greenhouse world, but at a pace far too rapid for life to adapt. The cooling of the poles marked the end of a remarkable chapter in Earth's history. The transition from a greenhouse world to the icy Earth we know today highlights the planet's ability to transform in response to even subtle shifts in climate. As we navigate a new era of rapid change, the story of the tropical poles reminds us of the fragility and resilience of life on Earth. The poles were once tropical, a land of dense forests, flowing rivers, and abundant life. Crocodiles swam through Arctic waters, turtles basked along riverbanks, and palms stretched toward the sky. Today, those landscapes exist only in the fossil record, hidden beneath layers of ice and rock. Over millions of years, the warmth faded, forests disappeared, rivers froze, and ice spread across the poles, reshaping the planet's northern and southern extremes. The vibrant ecosystems of the Eocene came to an end, leaving behind traces of a world now unrecognizable. The tropical poles were a fleeting chapter in Earth's deep history, a time when life thrived in places that now lie silent and frozen. If you enjoyed diving into the mysteries of lost species, don't forget to subscribe to Echoes of Extinction for more deep dives into the stories of creatures that once roamed the Earth. If you want to keep exploring the incredible rise and fall of prehistoric giants, click on the video on your screen right now. It's another fascinating look at extinction and tales of non-survival. Till next time, keep listening to Echoes of Extinction.